Hello everybody, let's do the check for understanding together. So I want to make a 5-character password. If I'm only using lowercase letters or digits 0 through 9, how many are possible? So this is straight up fundamental counting principle. I can imagine each of these is a spot where I could write a digit or a letter. So I could ask myself, how many options do I have for the first character in my password? And I know that there's 26 possible letters I could choose, or 10 possible digits. So 26 plus 10 gives me 36 possible options for the first character. And then the second character, I also have 36 options, because I didn't put any restrictions. I could have a password that's like A. So for each of these characters, there are 36 things that I might choose to write in that location. So that's going to be 36 to the power of 5. For B, and then in the answer form, I wanted you to actually write out 36, 36, 36, 36, 36. Okay, what about if the first 3 characters are digits and the rest can be anything else? So if the first 3 characters are digits, that means I no longer have 36 options. I only have 10 options for each of these. Namely, the options are 0 to 9, and there's 10 of those digits total. So the answer here would be 10 times 10 times 10, 36, 36. Okay, what if it's got to be the same forward and backward? So going back to all the options being available again, I know I've got all the options for the first character, all the options for the second, all the options for the third. But once I've chosen what I have for these 3, P, 4, Q, then for this character, I know it's got to match this one, because otherwise it wouldn't be the same forward and backward. And this one has to match that one. So I only have one. So once I've chosen these 3, I only have one option for what I could put here. There's no choice. And I only have one option for what I could put here. There's no choice. So here it's 36 to the 3rd power. And then what if my password is going to be either all letters or all numbers? So this is a situation where we have to count the possibilities separately. If it's all letters, then I've got 26 possibilities for each of the 5 letters. So it's 26 times 26 times 26 times 26 5 times. So that counts how many passwords if I'm using all letters. What if I'm using all numbers? In that case, each of my 5 characters has 10 options, so that's 10 to the 5th. And so if I want to know, this is all the passwords that use only letters, all the passwords that use only numbers. If I want all the passwords that use either letters or numbers exclusively, then I'd have to add those 2 together. So that's the answer to problem 1. Okay, this is a true story. My daughter really does love those Cars movies. Not number 2, just number 1 and 3. I think that's generally acknowledged as being the correct opinion to have. So some of her favorites. Let's count how many different characters there are. Lightning McQueen, Cruz, Jackson Storm, Sarge, Mater, Ramon, Bobby. So that's 7 different characters. So she likes to so there's 7 characters. She likes to line them up, but she's got this big truck in the movie. The truck is called Mac, and you can slide the little cars inside the Mac truck. But only 4 of them fit in a line here. So if I'm going to line them up, the question is, how many ways can I put them in a line? So again, how many options do I have for the first character I put in? I could put in any of the 7. And then how many options do I have for the next one? Well, I've already used 1, so there's 6 left. So I've got 6 options, and then 5, and then 4. So that right there counts how many ways I could choose 4 characters and put them in a line. Okay, she also loves to race them together, so she'll just, grab 2 of them and then race them around the living room. How many different race pairings are possible? Well, here, it just matters which 2 characters we choose. It doesn't matter which we grab first and which we grab second. So if I was going to say, the first person I grab, how many options? 7 options. The second character I grab, how many options? 6 options. This counts Jackson Storm versus Lightning McQueen as a different pairing than Lightning McQueen versus Jackson Storm. But I don't want to count those as different, so that's why I've got to divide it by 2.
Dad, I came here.
Oh, here she is. Yeah?
I came here because I heard you talking about Lightning McQueen.
Yeah. She heard me talking about Lightning McQueen. Okay. So this equation is the same thing as saying I have 7 characters and I want to choose 2 of them. So this notation, 7 choose 2, is a shorthand notation for this expression. But like I'm really trying to emphasize the logic of where the expression comes from, which is that you're finding all the ways of putting 2 things in an ordering and then dividing by how many of those orderings are really the same as each other. All right, last problem. I have a 3x3 grid. Let's draw it just so we can think about it. So here's a 3x3 grid. There's 9 boxes. I want to put the digits 0 to 9 into all the boxes. How many different grids are possible if all of the digits are different? Well, first let's observe there's 10 actual digits here, so one of the digits is going to get left out. If I start with 0, I can only make it up to 8, and then 9 doesn't get to be in the grid. So it's like I'm going to select amongst these digits and try and put 9 of the 10 of these into those boxes. Okay, so how many different grids are possible if the number of the digits are different? If all the digits are different. So you could imagine like remapping these so that they're all in a line. It's like this would be the top row, this would be the middle row, this would be the bottom row. So asking how many ways of putting numbers into a 3x3 grid is the same as asking how many ways to put 9 numbers in a line. It's like the same problem. And so same deal. I've got 10 options I could put here, and then 9 I could put there, and then 8, and then 7, 6, 5, 4, 3, 2, like that. And this is the same thing as 10 factorial. So that's part A. Then for part B, how many grids are possible if I want the 4 corners to be the same digit? All right, if the 4 corners are the same digit, so let's choose the corners first. So this corner could be anything, so that's 10. But then once I've chosen what digit the corner is going to be, the other corners have to be the same. So there's only one option I have for each of those once I've chosen this one. Okay, so what about for the rest of them? Well, I know that in the interior here, they could be any digits except the one I chose for the corner. So I've got 9 options I could put here because the only option that's excluded is the corner one. Okay, it says the middle ones don't have to be different from each other. So there's 9 options, 9 options, 9 options, 9 options. So this would be 10 times 9 to the 5th power. Okay, so that's B. And then for C, it says I want to color 3 squares in the 3x3 grid red. How many different patterns are possible? So what's tricky about this one is if you start approaching it by saying this one could be red or not red, that's like 2 choices. And if this one could be red or not red, that's 2 choices, 2 choices, 2 choices. But the problem is this dramatically overcounts because this way of counting has no way of adding the condition that only 3 of them are allowed to be red. Here I'm saying, potentially none of them could be red, or potentially all of them could be red. So this approach doesn't really count the thing that we want to be counting. So let's think about it this way. I want to color 3 squares. So let's think about it in terms of which locations. I know 3 of them are going to be red, so I'm going to make 3 choices, which is the first red location, which is the second red location, and which is the third red location. So let's number the locations. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 locations. So The first red location, I've got 9 options to choose from. So now let's pretend that I've chosen one of them. Color it red. For the next one I choose, I know I can't choose that one again, so I've got to choose one of the remaining 8. And so I'll choose my second red location. And then for my third red square, I'll choose one of the remaining 7 locations. Okay, but the problem with this is same thing that happens whenever we don't care about the ordering. Here, it doesn't matter if I chose location 6 and then 8 and then 1. That's the same pattern. That's the same visual pattern as if I'd chosen location 8 and then location 1 and then location 6. So it's like I've got to take the number of ways of putting 3 locations in some particular order and divide by the number of ways of reordering them, because those would all be the same. Because I just care how many locations did I end up with eventually. And this, of course, is the same as 9 choose 3. And this way of phrasing it feels very natural for the problem. I have 9 spots. I want to choose 3 of them to color in red, where the order doesn't matter. And then again, 9 choose 3 is shorthand for this expression. That's it.